A very good day to all of you. So regarding this, we are now talking about the PDF what I had provided to you, that is regarding the Jablonski diagram and the IR spectroscopy. So subtitle is understanding the photophysiological processes and the IR applications. Okay, so now what are the components of the Jablonski diagram? So basically it is the electronic state, okay, and it is having the ground state as S0 and excited singlet state as S1, S2 and S3. Thereafter the triplet states are T1, T2 and T3. Thereafter the vibrational states are there. Okay, now thereafter the transition and the processes are there. So what happens in the transition and the processes? So basically in the transition what happens? The absorption happens. Thereafter the vibrational relaxation happens. Internal conversion, that is also known as the IC, intersystem crossing happens. Fluorescence happens. Phosphorescence happens. Okay, now thereafter we will see the detailed mechanism of the fluorescence, and thereafter the detailed fluorescence mechanisms are there. Let's have a brief review of what has been written. Okay, so in this basically, so there is a graphical representation of the electronic states has been mentioned in this PDF and the transition between them. Thereafter the histological background has been mentioned by that this type of the diagram was given by Alexander Jablonski, and the importance in the phytophysics it's there. It is a critical for understanding the fluorescence and as well as the phosphorescence spectroscopy, and it is having the three type of the state. The ground state, that is called as the S0, excited state as S1, S2 and S3, triplet states T1, T2 and T3. Thereafter the vibrational levels are there. So multiple vibrational levels are covered under vibrational levels that include the sub levels within each of the electronic state. Thereafter the transition and the processes. Absorption, excitation happens in the absorption from S0, that is the ground state, to the higher singlet state. Thereafter the vibrational relaxation happens, that is nothing but the rapid non-radiative process to the lowest vibrational level. Thereafter the internal conversion happens, that is nothing but the transition between the electronic states of the state spun. Okay, multiplicity happens, that is called as the IC, that is nothing but the internal conversion. Thereafter the inter-system crossing happens, that is called as the ISC, that is the transition between a state of the different spin. And what happens in this, the transition state between the states of the different spin multiplicities happen. Okay, thereafter now fluorescence is there. So fluorescence, emission of the photon happens from S1 to S0. Phosphorescence, emission happens from T1 to S0, and this emission of phosphorescence is slower than the fluorescence. Thereafter the detailed explanation of fluorescence. So in this the mechanism is there: absorption, vibrational relaxation and emission. Thereafter the energy wavelength relationship is there. So emitted length has the lower wavelength, lower energy than the absorbed light. Thereafter the applications of the fluorescence spectroscopy are there. So all these things are there. Thereafter the detailed explanation of the fluorescence, that is the mechanism that is similar but involves triplet state. Now the difference from the fluorescence, the difference of the fluorescence with respect to the phosphorescence is that, and the slower process due to spin forbidden transitions happens in the fluorescence, but that doesn't happens with the phosphorescence. Okay, applications used in studying the longer lived states and in the material sciences. Thereafter now the importance and application of the Jablonski. So basically it is used for the fluorescence property. Thereafter the photochemistry, understanding the photochemical reactions. Thereafter the material sciences, development of the OLEDs and the fluorescent probes, environmental study of the atmospheric photochemical processes. So all these things happens. Thereafter now we will see about the different type of the derivatization techniques. Okay, what are the basically the derivatization techniques? Let's have a brief review regarding this derivatization techniques. So what is the importance, and thereafter all these things would be covered. Okay, I hope this is clear to all of you. So now in this case we will see about the basic things. Now in this we will see the derivatization to add the fluorophore. that happens in the fluorescence. So what is the purpose of derivatization? So that increases the sensitivity, selectivity, improves the detection limit, enhances the analytical procedures. Now the common fluorophores are known as the dancil chloride, fluorescein, isothiocyanate, FITC, thereafter the rhodamine, thereafter the naphthalene 2,3-dicarboxyl, that is called as the NDA, Texas red. All these things are the fluorophores. Okay, now the processes that includes the selection, thereafter the reaction conditions, conjugation reactions, purification and characterization. Okay, application that includes what is the application of this? So they are utilized in biological labeling, environmental analysis, diagnostic and pharmaceutical analysis. So all these things are there. Now one more thing is mentioned in this PDF is the partial energy diagram of sodium or potassium. So sodium is on the ground state, that is the 3s1, and the excited state is 3p1, second excited state is 4s1. Now the potassium is on the ground state, that is the 4s1, first excited state 4p1, second excited state 5s1. Excitation and relaxation in atoms, process of excitation and subsequent relaxation leads to what? Emission of light. Line spectrum is nothing but the discrete lines of the different wavelengths are there that are produced when the electron transition happens between the energy levels. Now what is the need for the gaseous state in the atomic spectroscopy? So that is the free atoms, distinct energy levels in the gaseous state are there, reduced collisional broadening is there, and that causes the clear spectral lines. Thereafter the efficient excitation, more excitation in the gaseous state happens. Consistent sample introduction ensures accurate measurement, simplified spectra analysis, easier analysis and interpretation. Now the Boltzmann equation is given by Ni by N is equivalent to Gi e raised to power minus Ei upon Kt upon Z, where Ni is the number of atoms in an excited molecule, where N is the number of electrons in the number of atoms in the molecule. Okay, all these things would be there. Thereafter one more thing is there. Now thereafter the Gi is the degeneracy of the energy level I, that is the number of the ways the energy levels can be achieved. Okay, Ei is the energy of the level I, and K is the Boltzmann constant, that is 1.38 into 10 raised to power 23 joules per Kelvin, and T is the absolute temperature, Z is the partial function and sum of all possible states. Okay, sum of all possible states. Thereafter the modified Boltzmann equation is given by Z is equivalent to summation of J Gj e raised to power Ej upon Kt. Now what are the things which affects the Boltzmann equation? That is the population of the excited state. So Boltzmann allows the calculation of the population of atoms in different energy states at higher energy, and the lower proportion of the atoms are in the excited state, which is crucial for measuring the spectral lines. Thereafter intensity of the spectral lines. Okay, so the number of atoms is directly proportional to the intensity of the excited state that undergoes transition from the lower energy state. So Boltzmann, what it does, Boltzmann helps these population, thereby protecting the intensity of the emitted or the absorbed light. Now what happens in the temperature dependence? Okay, let's see the temperature dependence. So in the temperature dependence, what it shows the excited state. The Boltzmann equation shows that the excited state is directly proportional to temperature. So the temperature increases, the excited state will increase. Okay, this is important for what? For controlling and understanding the conditions of the spectroscopic changes and the temperature, which is significantly affecting the spectral lines. Okay, thereafter the quantitative analysis is there. So quantitative atomic spectroscopy, knowing the population distribution, allows for the determination of the concentration of the elements in a sample. Thereafter the equation helps in converting the measured intensities into absolute population, and all these things are there, and thus into the concentration. Okay, the spectral line ratios, so the relative intensities of the different spectral lines from the same element can be used for determination of the temperature of the light source, and Boltzmann equation assists in providing the theoretical basis for this equations. Thereafter the thermodynamic equilibrium. So equation assumes the thermodynamic equilibrium, which is a good approximation in many atomic spectroscopic techniques. It provides the foundation for understanding the statistical mechanics behind the distribution of atomic population. So all these things are there, that is covered in this PDF. Thank you to all of you.